So I want to do this problem again that I did in the previous video, and that is finding the moment of inertia about the x-axis for this area, the area bounded by the x-axis, the x equals b, and this curve of y equals h over b cubed x cubed. All right, that's what we want to find. And so what we found in the previous video, using the strict definition of the moment of inertia about the x-axis, we would have to take a horizontal strip of area when we did our calculation. This ended up being a little bit ugly, totally doable, but is there another way? And the answer is yes. We can do these problems using what we call the parallel axis theorem. Now, we talked about moments of inertia in general physics, and so think about back to then when you did learn about the parallel axis theorem. So the idea is that for this application when we're talking about area, every area is going to have a centroid. And a lot of times the calculation of the moment of inertia when the axes pass through the centroid are already known. But then the question becomes, is there an easy way to think about the case where we have just simply moved that axis from passing through the centroid, but we kept the new axis parallel to the original one, and now we want to know that new moment of inertia? Well, that's what this expression is, and that's what the parallel axis theorem tells us. The idea is that our new moment of inertia, where the x-axis is not passing through the centroid, is equal to the moment of inertia where the x-axis does pass through the centroid, plus another term that talks about how the axis has been moved. For the x-axis, the axis would be moved in the y direction to stay parallel. So the distance that it's moved in the y direction squared times the total area. So this expression tells us how we can calculate the moment of inertia for a case where we're moving the axes from the centroid to another location. Now, in terms of differential form, this would just look really similar. Just replacing some of these terms by differentials. So what this is going to do is it's going to allow us to use a vertical strip. And this vertical strip has some moment of inertia about the x-axis that we can express in integral form. And we're going to do it using this parallel axis theorem. Now, just for you to know, as we consider each of the vertical strips does have a centroid where the original axis for the primed x-axis would have to pass through the middle of that strip in order to think about its moment of inertia when the axis passes through the centroid. You can see that this value in this picture would just be half of the y value. So that's going to be our dy, y over 2. So let's sort of think about how we're going to use this. Now, in your textbook, on the tables where they have different geometric shapes that I've already shown you, and we were using those to know where the centroid of different shapes were, there were also some expressions for moments of inertia. Now we're going to use those. So for a rectangular object, basically for a rectangle, that has a certain base and height, its moment of inertia when the axis passes through the centroid of that area is 1/12 the base times the height cubed. Now, I want you to think back to the moment of inertia of a rod. Now, that was a mass moment of inertia, but remember that it was 1/12 ml squared. And so, really, in this expression, b times h, which is the area, could be thought of as taking the place of the mass, and then you would be left with an h squared, L squared. So If these expressions look familiar, I think that's great because they should. And I think it also helps you to make a connection, and so it doesn't seem so totally crazy. So, for our particular uses, because we're actually not using a strict rectangle, but we're using sort of an increment of area, the way that we would change this is the base here is dx. And of course, the height is y. Okay? So let's put this together. The moment of inertia for about the x-axis could be found by taking the moment of inertia of dix, which is the one where the axis is where it is. But now let's substitute in this expression for the parallel axis theorem. And so we already know what the dix prime is. That's 1/12 dx times y cubed. Now, what's the dy squared? Remember, the dy squared was the distance that we've moved the axis, which corresponds to the distance to the centroid, which is y over 2. So that's going to be y over 2 squared. And then the dA is going to be equal to y dx. Now, there's a lot there. If we sort of add these, let's just kind of look at this right now. I'll do it over here. I'm going to put the dx and factor it out. I got a 1/12 y cubed plus a 1/4 y cubed, and then the dx is over here. Notice I could just add those. What's 1/12 and 1/4? And that's really nice because I can actually now add these two terms. I found that if I look at the coefficients, 1/12 plus 1/4 adds up to be 1/3. And I get the integral of dx times 1/3 y cubed. And so I also want you to think back to that example of the rod. And if you remember, the moment of inertia of the rod when we rotated about its end was 1/3 ml squared. So you see, it's actually related to things that we've done before. I think I'm going to change my pens because this is getting a little light. We do have to replace the y cubed. And so I'm going to get dx. I'm going to put the 1/3 out here. And then the y is h over b cubed. Oh, sorry. X cubed, all of that cubed. All right? And so I'm going to think I'm going to move up here because I have a little more room. So we got 1/3. And then I'm also going to have h cubed over b to the 9th. And then the integral of x to the 9th dx, and x goes from 0 to b. And when I integrate that, I'm going to get x to the 10 over 10, evaluated from 0 to b. And that's going to give me 1 over 30 h cubed over b to the 9th times b to the 10th. See where we're going with this? We're going to get the same expression. It's going to be 1/30 h cubed b. Well, I wrote it in a different order, but it doesn't change anything. I got exactly the same answer, which if I'm doing this right, I should get the same answer regardless of what method I use. But I think you might agree that the math, once I figured out how to write the increment of the moment of inertia, then the integration was a little bit easier and more straightforward. And in general now, every time we use a vertical strip, we can think of it as a small increment of the moment of inertia, and we can think of it as, in this case, is 1/3 the base, which is dx times y cubed. We can actually, oh, it didn't make it. Might make it as 1/3 dx times y cubed. So we can always use that. Or you can go through this work every time and remember that. All right, so two different ways to solve this moment of inertia problem. Using the parallel axis theorem, I think you'll see it used in the book when you read, because you're going to read it, right? And so it's just another way to do the calculation. It's similar to me in that when we were doing centroids, we always looked at, there were two different ways to accomplish the calculation, depending on what kind of strip you wanted to use, vertical or horizontal. And really, this is sort of exactly analogous to that situation.